You've done it? Have you guys done it? I think everybody did it in organic.
A little bit.
Huh?
It's hard enough.
Yeah. So, and then anytime you do one of those DNA mini prets, that's chromatography, right? So we're gonna do the exam 2 next Thursday. I switched it again because Dr. Smith switched his exam. Plus, looking at the schedule, it made sense just to do it earlier. Is that okay?
Really late.
Huh?
Late.
Early late. Yes, early late. So chromatography, what's the whole point of chromatography?
Separate stuff.
You nailed it. It's a separation process, right? And how does it separate? It's going to separate based on its on a substance's differential distribution between two phases. Okay. Can anybody tell me what the two phases we use in chromatography are? There's always two phases in chromatography. Anybody know what they are? One just sits there and one moves. Yeah, the mobile and stationary phase, right? So we're separating mixtures of substances based on the distribution between mobile phases and a stationary phase. Simple, right? So there's a number of different of methods of chromatography, and it's pretty self-explanatory. Liquid chromatography is going to use liquids as its mobile phase. Gas chromatography uses gas as its mobile phase, right? And then that can be broken down even further. In liquid chromatography, we have flat methods such as paper chromatography, which uses a paper like cellulose or something embedded in cellulose as its stationary phase. Thin layer chromatography, have you guys done this? In organic, I think you do thin layer chromatography. We got some thin layers, or high performance thin layer, or there's column methods, which is what we'll be doing in our lab. We'll do HPLC. I think, have you guys seen the demonstration that Ali does with the open column liquid chromatography, where you separate a blue dextrin, which is a big molecule, with a vitamin B6, which is, yellow or red, I guess, and that those separate, and you can watch it in the column separate based on size exclusion chromatography. So that's open chromatography, where you don't have the high pressures like you would with high performance liquid chromatography. There's a number of things this P could stand for. High performance, high pressure. My favorite is high priced liquid chromatography, because it's often an expensive process. Okay, so then there's even other ways you can divide up the categories of chromatography. Liquid chromatography, you could have liquid to solid, which is adsorption chromatography. Liquid-liquid chromatography, where you're going to partition the stationary phase is almost like a liquid in itself, and you're separating analytes based on partition coefficients based on the structure of the two liquids. And this includes reversed phase or stationary, or reverse phase or normal phase chromatography, or methods of partition chromatography. We'll see how that works. Size exclusion chromatography is what we saw that Ali demonstrates, where you separate the B6 and the blue dextrin. And that works because the stationary phase has little tiny pores that only small molecules can fit in, so they end up having to travel a much larger distance than the large molecules that go around the stationary phase. Then we have ion exchange, and that's where the analytes you're separating based on charge, and they're going to exchange with ions on the stationary phase. So that can be further branched off into cation, where you exchange cations, or anions, where you're going to exchange anions. So partitioning. So what is partitioning? So you have two immiscible phases here. You're going to mix a solute, and you can calculate its partition coefficient, basically, based on how much of it ends up in one versus the other. And these differential partition coefficients will allow you to separate different solutes. So in this example, there's 5 units in the upper phase, 5 units in the lower phase, so that it has like a KD of 1. And here we have 9 units that stays in the upper phase and only 1 unit partitions to the lower phase, which you have a KD of 9. So chromatography efficiency. So it's basically, what is efficiency is how well you do things, right? How efficient it is at separating the analytes. In this example, you can see it's highly efficient. You have really sharp peaks, clear division. This would be TLC here, clear division between the 2 spots of compounds. Whereas if you have a lower efficient chromatography such as this, you can see there's 2 peaks here, but you can't quantitatively calculate how much is of either one because they mix together here in the center, right? You don't have good efficient separation between the 2 analytes. And what's going to govern this efficiency is different retention of the analytes. So we're going to talk about retention next. And a way to measure the retention is called the capacity factor. And it's basically the capacity factor, it's the capacity of the stationary phase to retain a particular solute, right? So this will be one of the calculations you'll see on the test. And it's a simple calculation. So if we're doing liquid chromatography, capacity factor, that stands for K, is going to be equal to volume of elution subtracted by the void volume divided by the void volume, or the time of retention minus the time where you see that, how long it takes the injection part to get to the detector divided by the detector. And another term that we use is selectivity, is the ability of a chromatographic system to separate 2 solutes based on their differences in retention. So they're going to have different capacity factors if they're able to separate. So the mathematical term to measure the selectivity factor is given the term alpha, and it's going to be the capacity factor for one analyte divided by the other analyte. So if you have a capacity factor of 1, or not a capacity factor of 1, selectivity factor of 1, what kind of separation do you get? None, exactly. They're both eluting at exactly the same time because they both have the exact same capacity factor. So you want better separation than that. So, and this is figures showing you what these terms mean, basically. So for your capacity factor, the volume or time when you're eluting this analyte, and that's the center of the peak, is the VE, and that's going to be subtracted by the void volume. So when you do an injection for liquid chromatography, it's going to take a certain amount of time from that mobile phase where the injected agent is, or anything that's in that injection that doesn't stick to the column at all, is going to go through the column and appear at the detector. So normally you see it as a little bump on the chromatogram. So there's a certain amount of time for that mobile phase to go from where the injection is through the column and to the detector. You'll see a little bump. That's the V0. And to calculate capacity factor, it's the elution volume or time minus the void volume or time divided by the void volume or time. So it tells you basically the distance. Resolution is the capacity factor. Not resolution, capacity. Selectivity factor. Thank you. Is calculated like this, where you have the K1 divided by the K2. And if you notice, the void volume for the underneath term can be eliminated. You could just do V2 minus V0 divided by V1 minus V0 to give you the not resolution, selectivity factor. So you will see questions asking you to calculate these. I'll give you times and peak heights and everything to calculate capacity factor or the selectivity factor. Okay? So if you got questions on how to calculate, it's simple calculations, should be easy to do. Another simple calculation is the resolution, right? Resolution tells you how well separated the things are. So that's going to take into account the distance between peaks and the width of those peaks. And if you look at the equation for it, the resolution between peak 1 and 2 is going to be this. It's going to be the distance between those peaks divided by the average width of those peaks. All right, so it's just the width 2 plus width 1 divided by 2, and that gives you the average width of both peaks, the distance between those peaks. And in this example, width 1 is 0.4, width 2 is 0.8, so that's 1.2 divided by 2 is 0.6, and the distance, so the time, this is 3.4 it's coming off at, or 3.4 mils or 3.4 seconds. The second one comes off at 10.4. They don't give you units here, but you don't really need the units for this. And then, so it's 10.4 minus 3.4, which is 7 divided by 0.6. So it gives you a resolution of 11.6, because you get good separation between those two, and you get really good resolution. There's no overlap between these peaks at all. Not quite as good for the second two peaks, right? It's 2.7. So the lower the resolution, the closer are the peaks. So does that make sense? So this is another calculation, should be easy to do. Just remember the average width and the distance between the two. It kind of tells you the resolution. And here's a figure from a different book showing you the same thing, basically. I don't want to include sometimes. And then this next figure shows you what peaks look like with varying levels of resolution. So you have 0.4, 2 peaks are coming off here, but it looks like one peak, right? Very bad resolution here. To 0.5, 0.6, you start seeing the 2 separate peaks, but they're not very well resolved, are they? All right, 0.7, 0.8, 1, you start to see better, and really you want more than 1, so 1.25. You know, this is not quite down at the baseline. It's still overlap a little bit, but this is much better than of course, this would be or anything else. So that gives you an idea of putting number values, increasing resolution, seeing how those peaks begin to separate. Again, this is like poor resolution. This is good resolution, good column efficiency, nice sharp peaks, and good resolution due to column selectivity. They're not really sharp peaks, so that they stick to the column a little bit longer, but you still get good selectivity from that column. Stationary phase polarity. So this governs what's going to basically stick to that stationary phase and how well it's going to stick. Stationary phase is the component of the chromatographic separation. Selectivity is governed by this polarity, right? So what are the kind of forces that work with polarity? Do you remember? From like general chem, you can have, what does A describe? What are we seeing here with A? 2 things that don't look like they have any charge at all. They interact with each other and kind of induce an attraction. What kind of chemical force is that? It's not ionic. These aren't true ions. These are temporary dipoles generated from the interaction of those 2 non-polar substances. What is that called? Remember, van der Waals forces, right? We're looking at van der Waals forces here. So what are we looking at in B? Are dipole forces. And this is the example they show here. What is this? This is acetone, right? We got acetone generates dipoles, and you get dipole-dipole interactions. So these aren't ionic forces per se. They're just dipoles, dipole-dipole. And then the next force we're looking at here is what? Hydrogen bonding, which is a really strong dipole interaction. It's almost sharing of protons almost. And then we get our ionic forces, or electrostatic forces, where we're going to have ions are attracted to oppositely charged ions. And in this case, we have a tertiary nitrogen. What's the chemical for this? I forget. Do you know Tom? and then chloride as its counter ion. So, oh, I'm gonna kill myself with these chairs. So, and this shows you, this is not from your book, but it's from a different book, shows you the different types of chromatography that we have. So we have ion exchange chromatography, where we get separation based on the exchange of ions. This is an example of cation exchange. You're going to have a cation on your stationary phase associated with an anion that's fixed to that stationary phase. Cations in your solution are going to exchange with this. So you'll elute this, and your cation of your analyte of interest that you want to separate will stick to the column. Partition chromatography is going to separate based on the differences of partitions between two solutions or liquids, two liquid phases. So if you have something, you guys have heard of reverse phase chromatography? Ever? Well, we're going to talk about that. Reverse phase chromatography, the stationary phase, you have a lot of long hydrocarbons normally attached to it, like a C18 carbon means you have a hydrocarbon that has 18 carbons long that's covalently bound to silica particle, so that's what makes your stationary phase. So you have this coated on the column, all these hydrocarbons, and that is your stationary phase is hydrophobic. Normally for reverse phase chromatography, your mobile phase is hydrophilic or more polar. So your non-polar molecules are going to partition to that hydrophobic phase and be retained longer by the stationary phase. Does that make sense? Another example is absorption chromatography. So that is where you just use like pure silica or alumina. Probably the TLC that you did was absorption chromatography. So silica and alumina have all those hydroxyl groups. What are those hydroxyl groups good for? Or OH groups? Not hydroxyl. Do they have hydroxyl? But they have a lot of oxygens there available, right? So what's that going to be involved with? Yeah, they'll hydrogen bond. So you get adsorption. So really polar molecules in your mobile phase will be able to hydrogen bond or bind to the silica or the alumina on the absorption stationary phase, and they stick longer. And then size exclusion is what we were talking about before. Stationary phase has these small pores that the large molecules can't fit into. The small molecules can, so they get retained just because they have these little holes in the stationary phase that they'll fit into, the large molecules can't. So, and that's basically an example of gel permeation chromatography, and it's also called size exclusion chromatography. And like I just explained, stationary phase is filled with pores, large molecules too big to fit, so they're excluded. The small molecules permeate the stationary phase, and basically that gives them a much longer distance to travel because they go through the particles, and they can travel a much longer distance. They kind of get trapped in the particles, whereas the large particles just have a much shorter distance to travel before they can be eluted from the stationary phase. And this is an example of that. And this is what you'll see visually. And we can go do it in the lab anytime you guys want to watch the dextrin and the B6 separate. It's always a neat thing to watch. But the small molecules gets trapped, large molecules come straight out, and then eventually you can get the small molecules to come out too. The more mobile phase you add, they'll be carried out also. And this is the picture your book shows. And this isn't from your book, but this one is. I'm not a fan of this picture, I think. I try to include all the pictures, so hopefully one will resonate with you. So the different mechanisms, we already had a slide talking about this. We had adsorption, where we have interaction of the solute in the mobile phase and molecules at the surface of the solid particle. And that's going to be your silica and alumina. Two types of absorbents, nonpolar and polar. Polar can be acidic or basic, and most common are silica and alumina. And retention of the solutes requires displacement of absorbed solvent molecules. So you can kind of optimize your chromatography by either changing the stationary phase, or you can alter the composition of your mobile phase by altering its polarity, and that can, improve your resolution. And this shows you an example of a silica surface. You have all these OH groups on the silica, and polar groups that can hydrogen bond are really going to stick well to the silica. And here you got a hydrogen bond donor to this oxygen and a hydrogen bond acceptor, and so forth. It's going to really cause molecules like that to be retained. And you can get separation because, like, for example, here you have hexane as the solvent. Hexane is not very polar, right? It's just a 6-carbon molecule. And then we're separating these compounds. In this example, this is going to be retained the most, right? Do you see why? Because you can have a hydrogen bond or donor here, hydrogen bond acceptor, and a lot of places for hydrogen bonding interacting. This is going to be retained the longest. This will be retained the next longest based on, here you have a hydrogen bond acceptor and another hydrogen bond acceptor, no hydrogen bond donors. This will be retained the least because you only have one place for interaction here where you can accept hydrogen bonds. Does that make sense? So if I give you a bunch of molecules, you can, in a setup, you guys can tell me which one should come off first, second, or third, based on this kind of chromatography, right? So it should be simple stuff. So partition chromatography is where you have separation based on the differences in their distribution between two immiscible phases, like oil and water, right? Liquid-liquid chromatography, you have normal phase and reverse phase. And this is an important distinction between the two. You want to know this distinction for the exam. So normal phase, the phase support is coated with a polar substance. Oftentimes what you do is you take water and you take silica and you just coat it with water first. And then you use a non-polar mobile phase, and that's called normal phase chromatography. So in normal phase chromatography, analytes that are going to be retained are going to be highly soluble in the polar substance, right? So they'll be very polar. Reverse phase is the phase support's coated with a non-polar substance, and that's, like I was saying, C18 columns are reverse phase columns. You have 18 carbon length hydrocarbon covalently attached to a silica support. So non-polar substances are going to be retained longer because you're going to use a polar solvent for the mobile phase. Okay? And this shows you an example of normal phase chromatography. In this example, we coat the silica, you have a little phase of water around the silica, and molecules that are polar are going to, be retained the longest, whereas molecules that don't have a lot of polarity, such as this one, are going to be retained the least. This one would be retained the longest, right? You have a lot of polarity there. And then as this gets bigger and bigger with less polarity, you get less and less partition into this water phase that's around the silica support. And if you notice, the solvent is chloroform and methanol, so it's somewhat polar, but mostly non-polar, right? I guess. And then this shows you reverse phase chromatography. So you take a silica support and you're going to add these long chain hydrocarbons to it. This is a C8 column. So you can have there's a number of different stationary phases that are used for reverse phase chromatography. Most common are going to be C8, octosilane, meaning it's 8 carbons long. There's 18, C18s are very common. There's even phenyl rings where they attach phenyl rings to the saline. That can be used also, and they're all reverse phase. So for reverse phase chromatography, non-polar solutes are going to be able to be retained longer than polar solvents, and then you want to use a polar solvent for the mobile phase. For ion exchange chromatography, the stationary phase basically is going to possess a formal charge. For cation exchange, the stationary phase is going to have a negative charge, right? Because you're going to exchange cations. For anion exchange, stationary phase exchanges anions, so the stationary phase is going to be cationic, and you're exchanging an anion analyte with the counter anion that's on the stationary phase already. And cation exchange is the opposite. The cool thing about ion exchange chromatography is you can vary the pH of the mobile phase and differentially elute analytes based on their acidity or basicity, right? Remember pKa's? So if you have an acid with a pKa of 4, what charge is it at pH 6? An acidic compound? Yeah, what kind of charge would it have at pH 6? If its pKa is 4, it's good, at pH 4, it's 50% protonated and 50% deprotonated. So at pH 6, it'll be nearly 100% deprotonated, which means it'll carry a negative charge. Well, yeah, it's acidic, and an acidic compound is just something that's going to give up a proton, right? So you have HA to A plus H. So it gives up the proton. So, and if this the pKa equals 4. That means at pH 4, you have equal amounts of this and this, right? Do you guys remember Henderson-Hasselbalch equation? So at pH 6, most of it, nearly 100% of it, is going to be this anionic form. So if you wanted to separate this from another acid that, let's say, has a pKa of 2, what you do, or pKa of 1, let's say, what you do is at pH 6, you run it on the column, both anions are going to stick to the column. You change the pH to a pH of 2, which at a pH of 2, it'll protonate this anion, so that nearly 100% will be the protonated form. Will no longer be charged anymore. It's not going to stick to an anion exchange column anymore. Does that make sense? So it's a way you can differentially elute acidic or basic compounds just by varying the pH of the mobile phase. So pH variations, they increase ionization, will increase retention. Decrease the ionization will increase the elution of those. You can also vary the charge strength of the mobile phase, right? To differentially elute things. If you can stick the cation to it and then add a lot of sodium chloride, which has a lot of sodium, and those sodiums will then displace the cations that are on the column, and it's a way to elute cations, and vice versa, anions for chloride. So charge strength of the counter ion on the stationary phase are something that can be altered also. And this is an example of, anybody give me a guess what this is? What kind of chromatography this is? This is very specific. So what we're doing here is we're using a biological interaction to
This would be more like an amino acid sort of thing?
Yeah, well, sort of, but yeah. So you can use antibody. You can have antibodies bound, or if you want to purify an antibody, you have the antigens bound to a stationary phase. So this is right here, affinity chromatography. So it's using biological interactions between an analyte and its ligand. And you can capture, like in this case, it looks like they have a ligand bound on some kind of spacer arm on a stationary phase. If you want to purify its receptor, you run a mixture, your biological sample there that has a mixture of receptors, it'll bind to the ligand. You can elute it by just boosting the concentration of the ligand in the mobile phase, and that'll displace the bound ligands with the receptors and take those receptors off the column. An example of this is anybody heard of putting his tags on recombinant proteins? So polyhistidine will coordinate nickel. So what they do, you have a polyhist tag. If you want to have a recombinant protein, you add a bunch of histidines to the end or the front of that protein. And then when you purify the protein, all you have to do is put it on this nickel column. The histidines will coordinate the nickel and stick to the column and wash everything else out. So then you've basically purified it on the column, but how do you elute it from the column? Anybody give me a guess? I mean, you could, but that would alter the affinity for the histidine. You could protonate that histidine or deprotonate it. But more than that, does anybody remember the structure of histidine? What's the R group? It's a compound called imidazole. So basically, you just run a high concentration of imidazole through the solution. The imidazole will displace the polyhistidine tagged protein from the column, and the imidazole will then saturate that nickel column, and then you'll elute the column that way. But then you have this high salt concentration of a recombinant protein. How do you get rid of that high salt? Huh?
Ion exchange.
You could do ion exchange, but more common than not, because you have this big protein. Size exclusion chromatography, yeah. Because the ion exchange, because we're talking, the high salt we're talking about is imidazole. And that, you could vary the pH and get that to be ionic for sure. But then normally what you do is the size exchange chromatography, because you got a big protein you want to separate from a little imidazole. Okay? So things like that. So for biological samples, that a lot of times they might require some prep. And for our example of what we're going to do for reverse phase chromatography, we're going to have to extract the analytes or extract the proteins, because the proteins are going to be bad for our stationary phase. Complexity of biological sample matrix will affect the separation. And the interaction of the samples impurities with stationary phase reduces that resolving power. And not only that, but proteins a lot of times can just degrade your column as it goes. So saturation of chromatographic detection system will increase the noise of your system, because you keep seeing all these biological compounds coming off. It's going to decrease the sensitivity. You won't be able to detect what you're interested in. And then the interaction of the analyte of interest with a matrix components can also interfere. What are matrix components in blood that might interact with your analyte? Things such as albumin, things that naturally bind to analytes in your blood may cause matrix effects and decrease its interaction with the stationary phase. So poorly resolved components that interfere with the analysis will require some sample prep. And there's a number of different methods. You can have mechanical methods for initial isolation. So if you have solid samples, they must be prepared as a homogeneous solution or suspension where the analyte can be then isolated. Liquid samples can be treated to remove analytes sequestered in the matrix components. So you want to disrupt cells if you're going to do that, or precipitate proteins. For the lab we're going to do, it's going to have to be divided into 2 days, because we're going to prep our samples. And to prep the samples, the blood samples and the urine samples that we're going to do, we're going to precipitate proteins. We're going to do that with an acetone. So we're just going to saturate the solution with acetone. It's going to precipitate the proteins. We spin it down. Protein should be in a pellet at the bottom. We take the acetone top, and then we're going to just evaporate all of the acetone and water off of that. Okay, so then our analyte should be there, hopefully not too many proteins left over. And then, so we precipitate the proteins, we're going to centrifuge down, pellet those proteins, evaporate the analyte, then we'll resuspend our analytes in the mobile phase, and that'll decrease the amount of noise we're going to get altogether. A lot of times people, you might want to do like a initial isolation of the analyte. You can use a ZAD2 resin, silica, a C8 column, or ion exchange if you know the properties of the analyte you want to measure, you can kind of pre-purify it with column chromatography. Or a lot of times you can do extractions, liquid-liquid or liquid-solid partition extractions. Solvents should be immiscible with the matrix. So if you do a liquid-liquid, your analyte might go towards that like if you have proteins that you want to separate, like a hydrophobic compound for, that'll, use like a octane or hexane. The analyte will go to the octane or hexane or chloroform phase and not with the aqueous phase, and then you have it in that phase. So the solvent should be immiscible with the matrix, chemically compatible with the analyte. You don't want to extract it with something that's going to chemically alter the analyte. pH adjustments can be made to help remove acidic or basic components also. So if you're doing a liquid-liquid extraction, you want it to be neutrally charged, because if it's charged, it's going to stay in that aqueous phase for the most part. So you want to adjust the pH to give your analyte neutral charge, and then it'll extract to the non-polar solvent for the liquid-liquid extraction. So processing sample extracts, mini extracts are too dilute for direct chromatography. So like what we're going to do is we're going to concentrate via evaporation of the solvent. We're going to precipitate with acetone. There'll still be water there. We're just going to evaporate it all off with the vacufuge with the solvent. And then care should be used not to lose analyte, so you got to be sure that you're not going to lose analyte. What we're going to do to account for lost analyte is use an internal standard. We're going to spike our samples with the same amount of internal standard, which is a different analyte, and we'll test for that because we're going to know how much of that we have in the solution. And anything that's lost during this extraction and evaporation should be similar to what we're going to lose of the analyte we're going to measure, which is going to be creatinine. So water, anhydrous salts or desiccating salts can get rid of water, right? So adherence to the vessel. Sometimes if you have a protein or something, a lot of molecules can stick to the glassware. So a lot of times you have to treat that glassware so you don't lose your analyte. One example is like we used to make AAV at UF, and we would have to siliconize the tubes because that AAV would stick to the tubes. And we'd want as much of that virus as possible. So we'd treat our tubes. You don't want loss during evaporation, and you can also do a back extraction. So you extract it to a non-aqueous phase. You take that non-aqueous phase with your analyte, then you can back extract it to an aqueous phase by altering the pH of that aqueous phase to a pH where that analyte will be charged, and it'll all get sucked over to the analyte phase. If you have a small volume, that's one way to concentrate it. It's called a back extraction. Does that make sense? So this is your general setup for liquid chromatography, right? You're going to have some mobile phase supply, some way to control the flow of that mobile phase, a place for you to inject your sample, your stationary phase, or your columns, and then some way to detect the analytes coming off of those columns, and then a place for the waste. Or if it's a preparatory chromatography, you have a sample, a fraction collector that collects different fractions as it comes off the detector. Okay, and typically these days it's all computer controlled, which makes it easy, and there's some kind of detectors connected to the computer, and you can have a whole image of in the old days it'd be all on like paper that would feed out at a certain rate with a little pin mark that would read the detection. I think we actually have one of those machines back there, but it's pretty ugly. We don't use it, but it's old style liquid chromatography. But we have a computer, it records it all. Makes it look like the old style, but it's much easier and more you can manipulate the data more. No, that doesn't sound good. That's not what I meant, manipulate the data, but zoom in on peaks. You can record like the baseline, which is if you're having different, you don't always use the same mobile phase isocratic elution. You can have a varying elution. A lot of times it's good practice to just run mobile phase with the program that you have, and that can alter the detector response, changing that mobile phase. And that gives you a baseline that with the computer, you can subtract that baseline from all of the other analysis, so you can actually measure peak heights or areas under the curve of those peaks to get analytical results. So I don't mean like, what did I say, manipulate the data? No, I don't mean it in a devious way. I mean it in a useful way.
Does the computer nowadays control the supply?
Yes, computer controls the mobile phase, and you can gradient elutions. You can alter the rate, like the computer. Like for our HPLC, we can draw from 4 different mobile phases and have varying concentrations of those 4 phases the whole time during the chromatography program. So, and this is the figure from your book, basically shows a similar type setup. You have some sort of solvent reservoir that feeds the pump. The pump will draw from that. You can have a pre-column, sample introduction, a guard column, and then your analytical column. So what do you guys think the pre-column or the guard column would be good for? Yeah, like why do they have these other columns? I haven't talked about these at all yet.
Get rid of the junk that you don't want to screw up your expensive column.
Exactly. Yeah, get rid of the junk. Or saturate it with silica, because the mobile phase might strip away the silica and also, degrade your. So basically, both of these are both to protect your expensive analytical column. So either get rid of junk that's been in your that's in your sample, or saturate that mobile phase with the silicates so that you don't degrade your column. So does that make sense? So we don't have either of those on ours. So, but I bought all our columns off of eBay for like $70. I got about 12 of them from a lab surplus. It was like a gamble if they worked or not, because they didn't tell you if they worked. But luckily the C18 column works. I haven't tested any of the other ones. So,
Didn't pack it yourself.
Didn't pack it myself. No. Yeah, especially for HPLC. I've packed my own columns for size exclusion chromatography before, like a radio-labeled amyloid before, and packed my own column for that. So quantitation. So peak heights or peak areas are used to measure or to quantify the amount of analyte that's under that peak. Of course, peak area, the area under the curves, probably gives you the most accurate amount, but peak height is often easy and fast to do, and that's what you normally do. If you have good peaks, you'll use that. Minimizing retention volume while maximizing peak height results in the greatest assay sensitivity, right? Does that make sense? The longer it is retained on the column, the more diffusion you get across that column of your analyte, and the broader those peaks tend to be. Low flow rates and small support particle diameters will increase this sensitivity. So you'll notice on the columns they have different support diameters. The smaller, the better. You'll need a slow. You don't need a fast flow rate with the smaller particles. You get more surface area, right? But those small particles also increase the pressure that you're going to have going through that column, which will eventually degrade the column. But you use less. You can use less sample. They're more sensitive, and you faster assays. So liquid chromatography detectors are concentration dependent. So a lot of the times, like for ours, we're just looking at absorbance, and we just measure the absorbance of the analytes as they flow through the detector. So peak area detected by concentration-dependent detector is inversely proportional to the flow rate. So what does that mean, inversely proportional? Peak area detector. So the higher the flow rate, the less area you're going to see, right? Because it's the less amount of time it's going to be detecting it. Does that make sense? So for accuracy, for precision, you want to use peak area. So that's more precise weather. But for accuracy, they want you to use peak height if you have a good optimized protocol. You'll see with what we're doing, the last time anyways, the internal control is pretty broad, so I wasn't too pleased with that. So we're going to add a lot more than I did earlier this semester. Try to get higher peak heights for that. So. Standardization. So you can use an external standard. So, and that's we're gonna have an external standard where we just generate a calibration curve based on known concentrations. Okay, and we'll use peak height values with the known concentrations to generate a standard curve. And we've done this before, right? Protein assays, ELISAs. Just you have the known concentrations. You do linear regression. Then you plot your unknown peak height, and it'll tell you a concentration of your analyte. If everything's the same, right? So it's, ideally, you want the standards to have the same matrix makeup as your samples. But a lot of times, that's not easy. And this shows you another standard with the actual peaks that you might see on a liquid chromatography. So. We're going to use an internal standard. So internal standardization, this is going to account because we have to do an extraction. We got to get rid of those proteins from the sample so we don't destroy that expensive column I bought. So internal standard uses a compound similar to the analyte, controls for losses during the prep, injection, and detector variability. So we're going to spike all our standards and all our samples with the same amount of cimetidine when we measure our creatinine concentrations. Okay, so that peak should always be the same no matter what compared to the creatinine concentration. So added to both sample and standards before pre-treatment and the chromatography are performed. So then we get a ratio of the analyte we're interested in divided by the peak height of the internal standard. Okay, so we'll be doing this sort of graph here for our lab. And this shows you, this is from the other book, shows you what that would look like, right? So we have, again, the unknowns for the standard, the 10 micron, this is the analyte we're interested in, and the internal standard should always be the same, and then you get a ratio of the analyte of interest divided by the peak height of the internal standard. And we can plot that and come up with the concentration of the unknown based on the peak height of what we're measuring and the peak height of the internal standard. Another method of quantitation is called standard addition, where we add standard to the samples, add known amounts of standards to the samples, right? So and then we also have one without any standard added. And we can basically spike samples at different concentrations, and we measure the signal at concentration X, and we extrapolate, and we use the zero signal, and we assume that, you know, when it goes all the way down to here, it's zero, so then we can guess at what, you know, not guess, you calculate what the concentration is. So it involves preparing several solutions of the same sample that you're going to add standard to. Does that make sense? So, and then we were talking about elution modes. Isocratic elution is actually what we're going to be using in the lab, even though we have the ability to change the mobile phase. Isocratic elution is we have the same concentration of mobile phase everywhere throughout the elution during the chromatography process. Constant mobile phase composition. And it's simple, stable baseline. Remember what I was saying about manipulating the data? With isocratic elution, you don't have to be concerned too much about the baseline because it should be fairly stable. But for gradient elution, that can cause your baseline to vary. And there's different types of gradient elutions. You can have step versus linear or a whole host of other shapes. Can anybody give an example of we've already talked about a step elution a couple times, different ones. Like for ion exchange chromatography, altering the pH or salt content, that would be a step elution. Like you stick your cation at 1 pH, then just step the pH up or down to elute that ion from the ion exchange chromatography. So this is powerful. You can separate a wider range of compounds with gradient elution, and it's faster, and you can really optimize the sheep shapes, the peak shapes with this gradient elution. So you can get nice sharp peaks, which is better for quantitation, the sharper the peaks you have. So here's an example. This one is just a constant gradient elution. Might have peak shapes like this, but if you end up stepping it, you can really sharpen up these peaks, depending on what kind of analytes you're eluting, what kind of chromatography you're doing. And this just shows you that, isocratic, constant mobile phase concentration with a gradient, you have a change in the concentration. This is from that other book too. Don't worry about this one. It shows you the function of the computers during it. So consideration for selection of liquid chromatography type. So on the test, I'm going to give you some examples of things that you want to separate, and you're going to have to tell me what, you select which type of chromatography you'd want to separate those. Okay? So for size exclusion, you want to see the sizes are very different. You might want to use size exclusion chromatography. You might want to use ion exchange chromatography if your analyte you want to separate has an ionizable group with different pKa's if you want to separate two things, right? Adsorption, you got to know if it has hydrogen bonds. Does it form hydrogen bonds for absorption chromatography? Partition, it's not as well defined because all the forces are involved. You can really tweak the mobile phase and stationary phase with the partition chromatography. So, reverse phase chromatography, retention is favored by increasing nonpolar content of the analyte. The protein removal is normally necessary, so we're going to have to do that for ours. Right, we're going to remove the proteins. Again, this shows you reverse phase. This is a tyrosine. The phenyl group is going to really interact with the C18 column, whereas the carboxylic acid and amine groups are going to really interact with the water or the mobile phase, depending on what the mobile phase, the polar phase is, and so will the hydroxides. So stationary phase considerations. So separation is a function of both the characteristics of the stationary phases and the mobile phases. So you must rely on the manufacturers to produce the reliable, consistent solid phase material. So, which is why normally a lot of companies, and especially clinical labs, aren't going to be packing their own columns to make their stationary phase. They want something that's really consistent, and the companies that produce clinical assays with clinical grade columns have to really characterize and have good quality assurance and quality control in their manufacturing process. So you have to rely on the manufacturers to produce consistent solid phase materials. So during the prep of reverse phase columns, not all silanol groups react with the ODS groups on carrying that stationary phase. So you'll have some free saline groups, silanol groups. The resulting silanol groups are available for interaction with polar groups in the sample, and you don't want that for reverse phase chromatography, right? You want as few of these as possible. So a lot of times they'll treat the columns with trimethylchlorosaline to encap any of these unreacted silanol groups. So So, and you may need to adjust the mobile phase from previous reports based on lot numbers and, because these aren't always 100% consistent, right? If you get a report, if you're trying to follow somebody else's protocol, they get their elution at 5 minutes. Yours might vary a little bit from what they read, just based on your individual column. So you got to practice it a few times to get your protocol worked out. So, and this shows you the picture where you have the free Silanol groups and then the TMS gets capped there. So mobile phase consideration, changes in the mobile phase composition will have major effects on the selectivity and resolution. That's how you can get those good resolved peaks. So for reverse phase, you can change the type of organic solvent or adjust the mobile phase pH, ionic strength, or complexing ability. So what we're going to do in the lab is we're going to be separating creatinine. Creatinine is a basic compound. So we're going to lower the pH of our mobile phase, so nearly 100% of that is going to carry a positive charge. We're doing reverse phase chromatography, so a positively charged molecule is not going to want to stick. So we have to include a negatively charged compound with a long hydrocarbon, and it's called ion pair chromatography, and that'll be able we're including that in the mobile phase for basically a complexing ability, so it'll be able to be retained in the C18 column better that way. It's called ion pair. But you can alter the solvent strength, and there's a whole list. You can, the ability to elute solvents increases with the following order of solvent strengths. So of course it goes from methanol, which is going to be your most polar, to isopropanol, right, is less polar. So you can methanol, DMSO, ethanol, acetonitrile, tetrahydrofuran, dioxane, and isopropanol. So as you increase or decrease the polarity or increase the hydrophobicity of your solvent, your mobile phase will increase the ability to elute the solvents if you need to speed up the elution process. Does that make sense? So 10% increase in the fraction of organic solvent in water causes 2 to 3 times decrease in that retention. Ion suppression. So this is for ion exchange or for chromatography, or reverse phase, I guess. Altering the pH will greatly affect the solute partition into the nonpolar stationary phase, right? So this is estradiol 16-alpha glucuronide. So this is glucuronic acid, right? You added glucuronic acid to estradiol or estriol. So at really low pHs, right, you're going to have high retention because it's an acid. Low pHs, you increase the amount of protons available. More of this will be protonated, but as you decrease the pH, you really decrease the retention of that compound. And this is phenol. So phenol's got a fairly high retention value here, but then as you increase the pH to about 9 or so, the retention starts to drop off. So what's going on with phenol? Why doesn't it want to be retained in a hydrophobic type phase at these higher pHs? You don't remember the structure of phenol?
Is it in a ring?
Right, so this can be protonated, and then you can get like resonance, right? Or did I do that wrong? That was Ben's.
Just the H?
Yeah. Yeah. Right, so this can be deprotonated, makes it acidic. These electrons can be shared throughout that pi. You get that resonance stabilization of the negative charge there. You guys remember that? Which causes this hydroxy group to be acidic. Do you remember that from years ago? Which is why, that I think the pKa for phenol is around like 9 or 10 or so, or 8 or 9. And so you deprotonate that, and then once you're above here, that phenol ring is carrying a charge. So it's not gonna partition into that reverse phase. Does that make sense? So that just shows you can suppress that ions by altering the pH of your mobile phase. For our case, we're gonna increase the ionization of our creatinine by dropping the pH, but we're gonna have an ion pair there. So basic compounds, creatinine's a basic compounds. Modifications to the mobile phase are required. Remaining free silanol groups on the packing material are reactive with basic compounds. And amine modifiers can be added to the mobile phase to block the reactive silanol sites. Can lower the pH and high ionic strength you can use. We're going to be doing ion pair chromatography. The packing material has a limited pH range. If we wanted our creatinine to be purely not charged, the pH would have to be quite high, and it's not gonna support compatible with that reverse phase column. So we're going to be using ion pair chromatography. We're going to use a hydrophobic counterion to the charged analyte. So we're going to make the creatinine carry a positive charge, and we're just going to use SDS as our counterion. SDS has a negative charge and a long, 12 carbon long tail. So the creatinine and the SDS will be paired, and they'll be able to, stay with the reverse phase column, or be retained by the reverse phase column. Again, affinity chromatography, we have interacting biochemical pairs. Affinity ligand is going to be immobilized on a support and packed. Sample is then applied via an application buffer, and that elution occurs with the elution buffer. You can have a specific elution buffer, like we showed before, where you actually elute. You can have that ligand or analyte in the buffer, or in our case, the imidazole. Or you can have a general elution buffer where you alter the pH, which is going to alter that specific affinity interaction between those pairs. If you're going to separate enantiomers, so chromatography on conventional columns after derivation you can do with a chiral reagent. So if you derive, with the chiral reagent, you can separate those enantiomers, because then those will alter the specificity of those. Or you can perform chromatography on a conventional column with the use of a mobile phase that contains a chiral complexing reagent. So that chiral complexing reagent in the mobile phase will then alter which chiral compound is going to be eluted, because it will interact better with the chiral complexing reagent in the mobile phase. And another thing you can do is have chromatography on columns containing a chiral stationary phase. So it's one way to separate chiral compounds. So high-speed analysis, decreasing the size of the columns decreases the analysis time. The shorter the columns, smaller the volume of the columns, the smaller the amount of sample or mobile phase you have to go through, the less time it's going to take to get to the detector, right? So this requires smaller packing materials. So the smaller packing materials, the faster the reactions you can use, but it's going to limit your flow rates, which that can be good too. Increases the pressure though, right? The smaller the packing material is going to increase your pressure, and reduces the application lives. So those increased pressures really can interfere with your packing materials. So for solvent delivery, most common are reciprocating piston pumps. Minimizes solvent delivery pulses. You can have gradients where the solvents are mixed after passing through the pump, high pressure mixing, where you continually adjust, multiple pumps. Solvents mixed before the pump or low pressure mixing, and that you have continual adjustment of the times that proportioning valve allows a particular solvent to be pumped from multiple reservoirs. This is the sample introduction that you normally have. You've seen the HPLC 6-port valve. So Let's see if this goes through. Maybe it ends there. But this is what it looks like, right? So normally, this is your sample introduction. So we have on our HPLC system, we have a 20 microliter loop. So you can inject the sample here. The loop will hold exactly 20 microliters. So long as we have an excess of 20 microliters, we inject our sample, we fill that loop, and then coming out, that sample is going to go into a little waste container. So if we overfill the loop, we know we get our loop filled with 20 microliters of our sample. We want to have the same amount of sample for each thing that we're testing, right? And normally the eluent is coming in and then going out to the column. And this is being pumped in constantly. You inject your sample this way, you turn this, which changes the direction of the eluent from going from directly to the column to running through that sample loop, picking up 20 microliters of sample that you want, and then taking it to the column. So, nice, simple method of sample introductions. So the columns and connectors, columns the most important part of the separation, which is why we have these guard columns and pre-columns, right? So the guard column, like we said before, is packed with similar analytical column, and it'll collect the garbage that's coming out to protect your analytical column. Pre-column is going to be packed with silica, and that saturates that mobile phase with silicate, preventing the dissolution of the analytical column down the line. So both of these are cheap columns that you're going to add to your analytical system so you can extend the lifetime of your expensive analytical column. Does that make sense? And then detection systems, most frequently used, and that's what we use, is going to be your absorbance detection. It's the least sensitive also. Electrochemical detection is pretty sensitive, down to femtomolar to picomolar sensitivity. And what happens during this is it undergoes a reversible electron transfer. So, amperometric or coulometric detection, where you have electron transfer between an electrode and the analyte. In amperometric methods, you have 1 to 10% of the analyte react during that process, and you measure that current. Or coulometric, 100% of the analyte reacts, and you basically measure the amount of charge or the amount of current during the whole time of that transfer. But the differences with these is the analytes have to be redox reactive, right? They have to be able to accept or donate those electrons. Does that make sense? Or there's conductivity detection also. And then there's, of course, mass spec detection, which is the preferred method these days, where you have HPLC or chromatography tied to a mass spec, and you just detect the mass that's coming off. And you can even have MS detection, where you detect the mass coming off, and you can further degrade that mass into daughter ions and identify the components of that compound coming off. This is an example of just a absorbance detector on an HPLC system, where you have a flow cell, you have a reference just running the mobile phase, versus where the sample comes in and samples out, because you need something to zero that, and goes through that dual flow cell from the lamp, and you measure the absorbances of both. So, the percent transmittance, rather. The next thing we'll talk about is gas chromatography. So later on we'll be doing GC. And the difference with GC and LC is what? Well, there's lots of differences, but just the title, right? Gas chromatography uses a mobile phase that is in the gas state. Liquid chromatography uses a liquid mobile phase. Gas chromatography has a column and it uses an oven. So the compounds for gas chromatography have to be volatile, so you have to be able to get those compounds into the gas state to be able to be with the mobile phase. Retention time's temperature dependent. And typically what you do is you alter the temperature of that column to elute different analytes from that gas phase. Efficiency equals to production of narrow peaks. Resolution is, again, the ability to separate those peaks. Carrier gas can't react with the analytes that of interest, right? That should be an inert type gas. I think for our system we use helium. That's getting to be expensive because pure helium is getting hard to come by. A lot of people are using hydrogen now, which they're substituting hydrogen instead of helium, which Richard won't let us do because he doesn't want a big tank of hydrogen in the building. But it's a lot cheaper.
But if you can produce hydrogen, don't you just have the water separated from the water?
Yeah, you could have hydrogen producers to do that.
Just produce what you need, right?
They want to have helium though because they're worried about explosions. Even though we got plenty of sodium and potassium in the chem lab.
The purity has to be extremely
Yeah.
for these carriers. It's like ultra.
Yeah, it's ultra pure. I think our tank of helium was like $600 or something like that we have. So.
In the chemistry, like one of those chemistry labs, they had the hydrogen produced.
Over on the main campus?
No, at the USDA.
Oh, the USDA, they have a hydrogen,
They had the, yeah.
a hydrogen generator?
Mm-hmm.
Yeah.
Yeah.
So the stationary phases for gas chromatography either can be gas to solid or gas to liquid. You have like a liquid phase around a capillary, or gas to solid, you have typically use diatomous earth. So, and then typically you're going to need to derive your compounds, derivatization. What is this going to do?
Well, it's like an organic, you're going to do CO2, break it down.
Well, you don't want to break it down per se, because CO2 CO2 is very volatile, but you want to separate, you want to kind of keep the characteristics of the compound, but you want to make it more volatile so you can get it into the gas phase. So if you have a lot of like aldehyde groups or amine groups, you want to cap those with something that's hydrophobic so that compound will be easier to get into the gas phase. So you don't have hydrogen bonding interactions that's going to keep it, give it like a high boiling point. You want to lower the boiling point of whatever analytes you want to look at. Does that make sense? So the whole derivation process is, wrong way. Derivation process is just to make your compounds volatile in the analytes that you want to test for. Even though you're chemically altering them, you're not going to be able to measure them if you don't get them into the gas phase. So it also increases the sensitivity and decreases that partition coefficient between the nonpolar and polar phases. And an example is like barbiturate. You have these, nitrogens that can donate hydrogen bonds. You'll react them with methyl groups, and you basically cap the nitrogens with methyl groups, so they can no longer be hydrogen bond donators, and this is going to decrease the boiling point. So you can get this compound in the gas phase at a much cooler temperature than you can get this compound. Does that make sense?
Yeah, I think it's
So. And you can, what you do with gas chromatography, instead of like changing your mobile phase, is to alter the temperature of your column. You got your column in the oven, it pretty much has the same component. Your gas phase is always going to be that pure helium or hydrogen or whatever gas you're using. LabQuest sells little GCs that use the air, just ambient air. So you don't really have a gas source, it just uses air as the gas source. But you can alter the gradients of the temperature, and that'll alter how long different analytes are going to elute. If you have isothermal, you might get elution such as that, or if you have a linear increase in temperature, you can sharpen up the peaks, and whether you make it a concave increase in temperature or a convex, you can, optimize your resolution and everything of your peaks. So. Detectors, different detectors for gas chromatography. So thermal conductivity basically is going to measure the difference in ability to conduct heat. So as you're passing compounds through the gas, that's going to alter how much heat that gas can absorb as it goes through the detector. So basically, you have just the carrier gas in or the column effluent, and the difference in thermal conductivities between those two will tell you if you have analytes in the effluent coming off at a particular time. Does that make sense? So this just shows you these resistors here, the amount of resistance you get is going to be based on the amount of conductivity of the heat coming off of these. And the gas is going to have a different conductivity to a gas plus analyte. Does that make sense? Which will alter the amount of resistance passing through this thermal couple there. There's also flame ionization detection. So that elution is mixed with hydrogen and then burned. So this is the case you need hydrogen. So the electrode collects generated ions and generates a current proportional to the concentration. So for this, you introduce a hydrogen with a flame. The hydrogen comes in, you burn it, and then the ions coming off generate a current to the meter, and you can determine how much of that is there. So. And this, I think, is another picture of the flame ionization type detector. There's a nitrogen phosphorus detector. It's like a flame ionization detector, but an alkaline metal is introduced into the hydrogen flame. That's the only difference. In this case, it's rubidium or cesium bead that introduces that. And you can have electron capture, where you have beta particles beta particles collide with the carrier gas molecules, produce low energy electrons. And those electrons are collected on electrodes, and they'll produce like a standing current that you see. If you have chemicals with high electron affinity pass through that, they'll capture those electrons, and it'll reduce that standing current. So you'll be able to tell when when you have analytes coming off during that. So it kind of lowers the current. Other detections include mass spectrometry or Fourier transfer infrared spectrometer. So for mass spectrometry, basically what you do is you create ions from the molecules as they come off the column, or you just create ions of the molecules, and you analyze these ions based on the mass to charge ratio, which you often see as the M to Z. Okay, and this is your typical mass spectrum. These are all your mass to charge ratios. And this might show you a typical mass analyzer. So you have chromatography, will feed into an ion source, which will ionize analytes coming off the columns from your separation. That ion source then goes through a mass analyzer. There's a number of different types of mass analyzers they have. You've heard of quadrupole mass analyzers and ion trap mass analyzers. Basically separates those, it can analyze the mass of the ions coming from the ion source, typically based when they hit that detector. And I'll talk about different ways that it can do this. And this shows you can identify masses coming from different peaks from the chromatography. So you can choose to just look for one particular ion coming off. So you can just ignore everything except for the ions that you're interested in and quantify those. So if you only have a few analytes of interest, quantitative analysis, and their mass spectrum is known, you can just set the mass spectrometer to program it just to monitor those ions. So we could do that with our MS, but we don't have to, I guess. Isotope dilution mass spectrometry is a way to basically quantify the amount of mass that you have. So a compound labeled with a stable isotope can be used as an internal standard. So you basically you add a known amount of the isotope that you're interested in identifying, but you add a known amount of a mass isotope, right? So it's either going to be deuterated or a different mass compound where you have, like, typically I wanted to get quantify nicotine levels and have a deuterated standard that I know the concentration of. Because with our mass spectrometer, we just inject the sample into the GC. There's like no loop to inject a fixed amount. So we need some sort of internal standard like this to be able to detect concentration levels. The ability to quantify the compound relative to its isotopic species of a known fixed concentration is known as an isotope dilution analysis. So you have the isotope of a known amount mixed with your sample, and you run standards with the known amount and an unlabeled sample, so you can get the ratios of both that you would get with the standards. Keep that known amount always the same. And when you run your sample, you dope it with the known amount of the isotope. And based on the ratio between the normal ion peak and your isotopically labeled peak, because they'll have different masses based on the extra, neutrons there. Well, you can, based on those peak heights, you can quantify your unknown mass coming off. Mass spectrometers have several components. You have to have a vacuum for the most part. Place where a sample is introduced, you got to have some way to ionize that sample. Then you have to have some sort of filter out the masses or separate those masses. Some place that collect the ions, where you can amplify the signal of those ions hitting the detector in the system. This is an example. This is just your normal quadrupole. You have some sort of ion source. Masses come in here. Typically there's going to be a deflector here. So you create ions. You have a charge, repeller that's going to repel the ions down through this vacuum tube. And then these quadrupoles, basically you vary the charge on the quadrupoles, which will cause a varying magnetic field, cause the ions to spin down here. And based on the rate at which you're varying these, you can select for certain masses, only allowing certain masses to fly through the sensor to the detector. And then an electron multiplier adds to that signal. I think this shows you better the ion source. Sample comes in, gets ionized. In this case, it's an electron beam that ionizes the sample. Repeller has the same charge as the ions that's produced. Sends those through a focusing slit. So then you have an ion path going through the object split down through the mass filter or mass selector. And that was basically an example of an electron ion source, right? So for the electron impact ion source, the gas sample comes in, the repeller's here, you have an anode here, and then the electrons flow this way and will basically ionize the sample as they come in, and then they get repelled down through the mass filter down to the detector. Chemical ionization is a soft ionization technique which uses protons transferred to or abstracted from the gas phase analyte by a reagent gas molecule. Reagent gas is directed into a special source, so the source pressure is increased to about 0.1 torr. Electron beam ionizes the reagent gas and produces reactive species. You get collisions between the reactive reagent gas and the analyte, causes proton transfer, and then relatively little fragmentation occurs. So sometimes you want little fragmentation so you get an overall picture of that large mass of the main parent ion that you get. There's electrospray ionization, with the samples ionized at atmospheric pressure before introduction into the mass analyzer. Samples pass through a narrow metal fused silica. 3 to 5 kilovolts is applied, and the electrostatic forces of the liquid results in expulsion of charged droplets from the tip of the capillary. I got a picture of this like this. So basically, so the electrospray comes through here. You generate these charged particles. It gets charged there to 5 kilovolts of potential. Charged particles come through and they condense down to single ions, basically, that will be able to go through to the mass detector. And then the other form that's very similar is atmospheric pressure chemical ionization. It takes place again at atmospheric pressure. It involves the nebulizing and desolvation and uses the same sample extraction cones as electrospray ionization. But you don't apply voltage in the inlet capillary. You have a separate corona discharge needle. So here is where you get the voltage applied to generate those ions here. And for example, you have methanol, generates a charge here, and then that methanol will react with the mass, transferring the charge to the ion that you want, your analyte, and then you have the ionized charge with a new proton there that it generated from that methoxide, or not methoxide, the methanol ion. So, atmospheric pressure photoionization provides complementary approach to ESI. It differs from API primarily in 2 respects. It replaces the coronal discharge needle with an ultraviolet lamp that has about 10 EV krypton discharge lamp to generate phase ions via photoionization, and additional reagent gas that is easily ionized, such as toluene. So as with APCI and CI, once the primary ions are produced from the toluene, they undergo a series of non-ion molecule reactions that eventually will result in the ionization of the analyte molecules. So, and then there's inductively coupled plasma, which is the hard ionization. This is the type of mass spectrometry where you just break it down to its basic elemental particles, so you get elemental analysis of something when you do inductively coupled plasma ionization. So for the most part, in a clinical lab, you're not going to be doing this type of stuff. This is stuff you do like with geology and things like that, right?
Yeah, it's for metals.
Yeah. So, but you might see some matrix-assisted laser desorption ionization. If you guys ever seen this?
I'm giving a talk tomorrow.
On this?
Yeah, quality talk.
Yeah. So you know what this is then, right? Yeah, so basically, it's used often for proteomics. You can separate proteins via 2D gel electrophoresis. Cut the protein, the spot out of interest, which is going to contain one protein. Oftentimes, they'll do a trypsin digest with that. Then you purify that spot from after you trypsinize. You purify the spot, trypsinize it, which is break down that protein to its trypsinized fragments. And then you're going to purify that, mix it with a matrix material, and deposit it on a solid metal surface. So you have this matrix material that's deposited onto the solid metal surface, hit it with the laser, ionizes it, and kind of knocks it off its metal plate because you have a repeller behind here, and it will force it into the mass analyzer. So there's this matrix-assisted laser desorption ionization, and then also, have you ever used surface-enhanced desorption ionization? It's very similar, but instead of just taking all the analytes of interest, it's basically like affinity chromatography. The surface, where are we? Surface is coated with something that'll increase the affinity for the analyte that you're interested in. So. Different classes of mass spectrometers. So we have beam type instruments and trapping type instruments. So your beam type instruments have a constant beam going through that mass filter, or trapping type, you have the ions get spatially confined to a certain region, and then you can elute those ions at specific mass masses that you want. And these are called ion traps versus beams are more common than not, but these are really becoming more and more popular as they increase in your, get better at it. They're bench top ion traps that are really useful. But one of the most common type, what we have here is called a quadrupole mass filter. So they lag behind the magnetic sector instruments in terms of the sensitivity, higher mass capabilities, resolution, and mass accuracy, because you can't, I mean, they're basically mass filters. You can filter out different ranges of mass. You can't get it narrowed down to specific masses. But their attractive and practical mix of features include they're easy to use, they're flexible, adequate performance for most of applications like what we're going to use in the clinical lab. They're low cost for the most part. And we got ours for $5,000, including the GC, but you'll see it's old. I think we use Windows 2000 to run it. And non-critical site requirements, highly developed software systems for use. And this is what they look like. There's 4 poles, and basically you alter the magnetic field around these poles. Charges on the rods are constantly altered, causing oscillations in the ions. You get these oscillations. And basically the rate of oscillations, you can use these to filter out. You'll develop these oscillations, use these to filter out specific masses that you want to filter out. You can run the sample, run the whole range of masses where you let the whole range of different masses come out and you know at what point they're coming out. Or you can select for one particular mass and just filter everything else out. Everything else will be expunged out to the side and you'll only let the one type, one mass or charge to mass ratio through. So this is your magnetic separation. This is what I remember learning way back in general chem, where you have a source and then you have some kind of curve, you know, this magnetic field that'll alter, you know, which masses are selected for to go through that collector beam. So I don't think I've ever seen these mass specs. Have you, Tom? Yeah. So I've only seen the.
Really specialized form experiment.
Yeah. I've always only seen the quadrupole and the ion trap and TOF. So the time of flight, which is this. If you're familiar with this, right? So a lot of times it's multi-TOF, so it's matrix-assisted laser desorption on a plate. Ionize those samples. They're going to fly down a vacuum tube based on their mass and charge ratios. The smallest ones with the highest charge will hit the detector first. Largest ones with the lowest charge will hit the detector last, and you can see how that when they hit the detector, it creates an electronic current. You can detect when they're hitting that detector. So quadrupole ion trap is used for GC HPLC detectors, relatively compact, inexpensive, versatile. So this is what you'll see a lot of these days in like my old department at UF. They had a lot of these, or a couple of these. Excellent for exploratory studies, useful for structural characterization and for sample identification, because you can trap the ions and you can really alter that magnetic field and cause those ions to break down to their daughter ions and break them down even further the longer time you send them in that trap. So the radio field is the RF field of the ion traps designed to trap the ions in 3 dimensions rather than to allow the ions to pass through like a quadrupole mass filter, which confines the ions into the 2 dimensions. Ions with the trap can then be manipulated to disassociate them into characteristic fragments and injected to generate a mass spectrum. So trap the ions, you can let them through to see what the parent masses are, or you can have them trapped in there. You can manipulate that radio field, radiomagnetic field, and disintegrate them in the ion trap and then elute and see what daughter ions come off. So almost like a MS-MS type reaction. And this is a picture from the other book that shows you ion trap type surface. So, and this is a little cartoon showing you the ions trapped in that three-dimensional space. So the ion cyclone resonance is based on the principle that ions immersed in a magnetic field undergo circular motion. Uses a high field 3 to 12 Tesla superconducting magnet within this field, and within a high vacuum is mounted a cell typically composed of 6 metal electrodes arranged as the faces of a cube, and the ions are suspended inside the cell and undergo cyclotronic motion, which keeps them from being lost radially, and the combination of electric and magnetic fields keeps the ions confined within the cell, and then the Fourier transform is used to extract the mass spectrum from the raw signal. And those aren't as common as the ion trap, quadrupole ion traps. And this is an example of a mass spec system where you have two different ways to filter out the masses. First, you have an ion source, has one analyzer, which could be a quadrupole. Then you send those ions through a collision chamber, which will break them up into daughter ions even further. And then separate those, and you can detect everything at the end. So first you can just run through the one to get the parent masses, collision them, and then measure the ions that come off from the daughter ions. So you can break it down and really determine structure of ions coming through. And then this last one is just an example of an MSMS with a quadrupole tied to a time of flight type detector. So, so argon's a heavy gas. Your ions introduced to the quadrupole, gets filtered out, gets broken down into the daughter ions, then goes to the time of flight type device. The repeller sends them down the time of flight tube, and it measures, the masses at the end of that tube. And that's it for the chromatography mass spec.